Recording is on.
Awesome. Okay. So welcome back. Uh, Before I start, are there any questions on what we did last time? All right. So of course, as before, you can ask during the session, and let me recall what we did. We took a field, um, FP, the field of residues of modulo P integers, and we took phi to be a polynomial over the field of degree n, let's say bigger than 1, and phi is prime. Prime meaning that you cannot write it as a product of two non-constant polynomials. And then we did a construction that is completely analogous to FP, that is, we denoted it as eventually as f p to the n, and this is the collection of all polynomials R that can be obtained as a residue of a long division modulo phi, long division of a polynomial by phi. So this is Rx, let's say sum ai x to the I equals 0 up to n minus or up to k, such that k is smaller than n, and the AIs are in F. And on this set, we saw that a plus modulo phi and multiplication modulo phi turns it into a field. This is quite surprising, maybe, for seeing it for the first time. And so FPN is a field with a p to the n elements. And moreover, F, namely FP, can be embedded naturally in FP to the n. How? Because this polynomial R, you can also pick it to be some A, some constant polynomial A, where A is in the field. So all the elements in the field are, in fact, in FP to the n, and all the arithmetic that existed in FP is extended to FP to the n. So when you do arithmetic of, let's say, A, and if you have B, then it's the same, multiplying the polynomial Rx equals A and Sx equals B in Fp to the n is the same as multiplying them as in Fp, namely multiplying and taking modulo P, and then putting them as constant polynomial, or putting the result as constant polynomial. So this is called a field extension.
Can you say it again?
And now, yes, and now, since Fp is a subfield of Fp to the n, and phi is a polynomial over Fp, like any field extension, I mean, if I give you a polynomial over the real numbers, you can consider it as a polynomial over the complex numbers, because the complex numbers extend the real numbers. We can consider phi as a polynomial in fp to the n, and I will take another variable here, x, big X, to disambiguate, because we use the small x for other purposes, namely for the remainders polynomials Rx. So now, if I consider phi as a polynomial in this polynomial over Fp, I attach to it a big variable x, big X. But the coefficients of phi, whatever they are, let's say phi x is sum phi I x to the I, then phi with big X is going to be sum phi I big X to the I. So I didn't do anything, it's like complete formality. Well, okay. So now I have a polynomial over fp to the n. Over fp, phi was a prime polynomial. Namely, in particular, it means that it doesn't have any roots, because then you can factor, if it had root, you could have factored this polynomial in a non-trivial way. However, what happens? So here in this new kind of weird field fp to the n, the elements are themselves polynomials. And in particular, I have the polynomial, let me call it alpha x equals x. This is a polynomial, so alpha is an element in the field fp to the n. And like any element in a field and a polynomial over this field, I can substitute the element into the polynomial. So we can do, I have the writing of this is you have phi with big X, and now you substitute big X equals alpha. And alpha, I remind you, is alpha of X is equal to X. So I substitute, instead of big X, I substitute small x. What I get is phi with small x. And this is this needs to be like with any substitution. If you take a polynomial over a field and you substitute an element in the field into the variable of the polynomial, you get, as a result, an element in the field. So this phi x needs to be considered as an element in fp to the n. But in fp to the n, we do addition and multiplication modulo phi. Modulo phi, you can think of it as modulo phi small x. And phi small x modulo phi small x is equal to 0. So what did I get? Now, it means that this element, alpha x equals x, is a root of phi with big X over the new field, the new extended field fp to the n. This means that I can write phi x equals x minus the root times some other polynomial, let's say phi prime of big X. And this is a kind of a magic. It's a, you can consider it as a meta trick. I didn't have a I didn't have a root of phi in the small field, and I extended it, and now I have in the bigger field I have a root. And so this is an insight that is very important for understanding finite fields. Any questions on this so far? It's not a trivial thing to wrap your head around. Yeah. Okay. So let me do it because this is relevant for any field. Let me do it with the real numbers. It's not a finite field, but everything we did is valid for any field. And I take phi small x to be the polynomial x squared plus 1. This is prime of degree 2. Why is it prime? Because, well, for polynomial of degree 2, if it doesn't have any roots, then it has to be prime, because the only way you can factor a polynomial of degree 2 into product of two things is x minus alpha x minus beta. So if you don't have any alpha beta, where alpha and beta are roots, so this is a prime polynomial. Now I do the remainders. F, we called it, I think, f phi or fx phi sub phi. This is the set of all remainders if you do division modulo phi. But if you do division modulo phi, the remainder can only be a polynomial of degree at most 1. So this is the set basically of a plus x, or sorry, a plus x, sorry, a plus bx. So in fact, I can do like this collection of all a plus bx such that a and b are real numbers. And it could be that that b is 0 or that a is 0. This is the collection of all remainders if you do modulo phi. And now I look at this collection. On this collection, I have operations: addition modulo phi and multiplication modulo phi. And if I do a plus bx times c, so now I consider the polynomial phi with big variable. Okay, phi with big variable, and now I substitute the polynomial alpha x equals x. Well, okay, I substitute alpha x, I substitute instead of big X, I substitute alpha x. I get, well, I get x squared plus 1. And x squared plus 1 is equal to 0 modulo x squared plus 1. What I got here, in fact, here, this phi fx sub phi is some kind of version of the complex numbers. If you do addition and multiplication modulo phi of 1 degree polynomials, you will see that this guy x behaves like the imaginary number I. This because x squared plus 1 is equal to 0, it means it's the same thing as saying that x squared is equal to -1. So in fact, this small x functions as the imaginary number. It's just a new notation. And this is the reason that once I substitute small x, I mean, namely alpha x equals small x, into the new polynomial over the new field, now I have a root, because x squared plus 1, in fact, is x minus I, x plus I, over the complex numbers. Okay? So this is maybe, I hope that this is a bit more clear now. But in fact, the trick itself is a meta trick. It's like I forced a field that extends the new field, but it now it has a root. It has a root of the polynomial by design. It's not well, okay. Theorem for any polynomial f let's say fp, but it's not again, it's not restricted to fp, just that we will use it for fp. There exists n such that or maybe big N, such that over fp to the n, f factors or decomposes to linear factors. That is, I can write f over this new extended field. I can write f as lambda times x minus alpha 1 up to x minus alpha k, where alpha 1 up to alpha k are elements in the new field fp to the n. And let's say k is the degree of f. Okay, it's kind of a miracle, but in fact, it's not so hard to prove this theorem, because what do? You take a prime factor, let's say proof sketch. Take prime factor of f, i.e. f is equal to phi times whatever, f1 or f prime, where phi is prime. Now you do the trick that we did. So you consider f p x modulo this prime polynomial phi. And this is your new field f1. Over this new field, over f1, the polynomial f has a root because phi has a root. So you take f and you extract a root out of it, so it's like x minus this root. So over f1, you write f, let's say f big X equals x minus this root times some polynomial g. And now you repeat, now G, you take a prime factor of G, and you extend the field F1 into a field F2. And then G will have a root into in this field F2 and so on. So this process terminates because the degree of the polynomial is finite. And by that, you are able to extend the field up to a level where all the roots of the original polynomial exist in the extension. And one of the things I want to do today is to show you why is it useful for practical purposes, not just for this. It may sound like some kind of a grand theory. So first example, if I have fx equals x to the n minus 1, then there exists some n such that x to the n minus 1 is equal to x minus alpha 1 up to x minus alpha n over fp to the n. Okay? Alpha 1 up to alpha n are denoted mu n of fp, and this is called a nth roots of unity. It's roots of unity because each of them satisfy alpha to the n, alpha I to the n equals 1. Okay? If you do the calculation over the complex numbers, what you will get over C, what you will get is you divide the circle into n different equal parts. Let's say to 3 parts. And each of these points on the unit circle will be a root of unity. This is n equals 3. But what we did allows us to do it over prime fields. So I take a prime field, and now I can extend it into some field in which all the roots of the polynomial x to the n minus 1 exist. Now observe mu n fp is a group. Why? Take 2 elements, let's say alpha and beta are 2 nth roots of unity. Then if I take alpha times beta, I need to see that alpha times beta is again an nth roots of unity. So I raise it to the power of n, but raising it is the same as doing alpha to the n times beta to the n, and alpha is alpha to the n is 1, beta to the n is 1, so this is 1 times 1 equals 1. Similarly, if I take alpha minus 1, it's also going to be an nth roots of unity, because if I raise it to the power of n, it's the same thing as doing alpha to the n and then taking inverse. And alpha to the n is 1, and the inverse of 1 is 1. Moreover, say theorem, mu n of fp is a cyclic group. And here I don't really prove, but the proof is because mu n of fp is a subset of the multiplicative group of some extended field. And the multiplicative group of any finite field is a cyclic group. This is kind of a big theorem. So in a subgroup of a cyclic group is cyclic. So this means W such that mu n of Fp is generated by W is called a primitive. So primitive nth root of unity is some guy such that W to the 0, W square up to W n minus 1 is going to be the entire description of the group of n roots of unity. Okay. Questions so far? I should have said maybe in the beginning. I know it is. It may be somewhat hard to digest in one go. So if it is a bit hard, try to kind of listen to the music, and you will have all the details in the book to check. And for those of you who saw these things a bit before, I think that it should be possible to follow most of the details.
Yeah, I mean, we already heard that people like to go back and rewatch some parts of the lessons. That's why we record them. So don't be worried, guys, if you don't understand this on the first time. But meanwhile, we also had a question. Leo was raising hand. If we have a minute to take a question from
Yeah,
him.
yeah. Then go on.
Yes, I was like confused what alpha x is.
Alpha here. If alpha and beta are nth roots of unity.
No, I mean the very beginning part. So I get lost from that part actually.
Oh,
Yeah, because I
in
don't get
this,
why is there is alpha, and I didn't see the
I
definition.
mean,
So yes, that's
alpha is just a notation. So what I did, I took the whole construction of this Fp to the n is, I mean, as a set, it's a set of polynomials, right? Polynomials of degree less than n, right?
yeah,
And
yeah.
and the operations are a bit weird because you do addition and multiplication modulo phi. But as a set, it's just polynomials of degree less than n, and we assume n is bigger than 1. So I have a polynomial that I denote as alpha that is simply the polynomial x, right?
Okay.
Okay. Now I said phi is a polynomial over the original field Fp, but the original field Fp is contained in a bigger field, Fp to the n.
How can phi is
So I can
sorry? How can phi is like element from the original field? I mean, like phi should be a polynomial, right?
because I mean, how Fp is embedded into Fp to the n, this is as constant polynomials. You take A in Fp, you can consider it as the polynomial Rx equals A. Right? It's a legitimate polynomial.
Okay.
Okay, so this means, but this is a general principle. Whenever you have a field extension and you have a polynomial over the small field, you can consider this polynomial over the big field because all the coefficients of the polynomial are in the small field, And you can think of the small field as embedded into the big field. You see?
Yeah, yeah, I can say like a small field is embedded into the big field, but here you define like phi x within the FP, but FP is a small field, right?
Yeah, but
Yeah.
FP to the n is a big field.
Yes. Okay. Oh, yes. Okay. Yes.
Okay, so now I want to consider phi over the big field, FP to the n. Now, to disambiguate, I write phi with a variable big X instead of small x, because in the definition of elements of FP to the n, we use small x. You follow?
Yeah. 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 Yeah.
Okay, so now I have a new I have a new polynomial. Technically, it's a new polynomial, even though the coefficients are the same. But now it has a big variable x, and it is considered over the big field fp to the n.
Yes.
Okay, and now, just like with any polynomial over any field, if I give you an element in the field, you can substitute this element instead of the variable of the polynomial. Okay,
Yeah. Yes.
so
Yes. Yes.
I take the big polynomial phi x, and I substitute, instead of its a variable, I substitute the element in the field alpha x, alpha small x.
Yeah.
I am allowed to do. I have to be allowed to do it. It's like a basic operation of a polynomial over a field, right?
Yes.
Okay. What happens when I do that? It's because alpha x is simply x, small x. What happens is that I get phi of small x. But phi of small x is equal to 0 in fp to the n, because I do modulo phi.
Yeah.
Okay, so I have found an element alpha x equals x that is a root of this polynomial phi big x. So now the polynomial phi that was prime and did not have any root, now it has a root. Over the extended field, it has a root. And the analogy is, you take x squared plus 1 over the real numbers. It's not, it does not have any root, but once you extend it, and in fact the complex numbers are exactly the construction we did. It's like
Okay.
all the remainder polynomials with modulo phi arithmetic. Then the variable x is like I. It behaves like I, because if x squared plus 1 is equal to 0, then x squared is equal to minus 1. So you see, so now, so we extended, and you can repeat, the theorem said that you can repeat this thing. So any polynomial, you can extend the original field enough so that this polynomial has all the roots it can have. Okay?
Yes.
So now I do this for a specific polynomial, x to the n minus 1. And I find that the elements of the roots of this polynomial, in whatever extension they exist in, when it's completely factors into linear polynomials, product of linear polynomials, these roots are in fact a group. And moreover, proposition, if the GCD of P and N is 1, namely if P does not, I mean, it's the same thing as saying P does not divide N, then the size of the group of N roots of unity is exactly N. Namely, all the roots, i.e., all roots of x to the n minus 1 are different. And a proof sketch. Otherwise, if I had two roots of x to the n that are equal, say, because it could happen, right, for general polynomials, say, alpha 1 equals alpha 2 equals alpha in mu n, then I could write x to the n minus 1, I could write it as x minus alpha square times some other polynomial gx, i.e., alpha is a root of x to the n minus 1 and of the derivative, the formal derivative of x to the n minus 1, that is nx to the n minus 1. So this is in general, if you have a double root, then it has to be a double root is the same as a root that is also a root of the derivative. And so, Lee, can you mute your? And so a double root has to be a root of the derivative, and if n is prime to p, and alpha cannot be 0 because it has to be a root of unity. It has to be the nth power of it has to be 1, and n is prime to p, so p does not divide n. So alpha is not a root of the derivative nx to the n minus 1. And that's a contradiction. So this is the group of n roots of unity. Now, I have one more piece of technology that we need in order to do this fast Fourier transform. And this is called Lagrange interpolation. Okay, so what is this Lagrange interpolation business? Here it is instructive, I think, to go back to Euclid. So Euclid said between any two points to P1 equals x1, y1, P2 equals x2, y2. In the Euclidean plane, this is, we denote it as R2, there exists a unique line that passes through these points. How do you know it? Well, okay, you can, here for Euclid, it was even without coordinates, it was like an axiom. But in fact, with coordinates, we can turn this axiom into a proposition that can be easily proved, because a line has this equation y equals ax plus b. And if I know that it passes through P1 and P2, then I have two equations in two variables. I have y1 equals ax1 plus b, y2 equals ax2 plus b. And they are unique a and b such that these two equations are satisfied. And so if we take f equals fp, so now I consider the FP plane. The FP plane, FP align in the FP plane, this is FP square, is the set x comma y in FP square such that y equals ax plus b for some fixed a and b in FP. So you see this, the whole, if I'm able to define the notion, in this case, the notion of a line in terms of a polynomial equation, then it makes sense over any field. I don't need to have a geometric interpretation over it. So this is a line over FP, and the same insight of Euclid will be true for the line over FP, because here as well, between any 2 points, P1 and P2 in FP square, there exists one line, right? Why? Because you take the same equations. P1 and P2 are now x1, y1, x2, y2, but in FP square, not in R square. And you write the same equations, and you find out that there is a unique solution, A and B, and so you get a line. You get a line by this definition. Is this clear, this idea? I don't understand the question, Marvel. Which calculation do you refer to?
It was a while ago, and I'm not sure if Marvel is still with us. Seems like he left already.
Okay. So please don't be shy in raising a hand. I just don't see the chat that often. So what I'm saying here is that this is in fact a wider phenomena. This is a theorem. Given a field, F, and endpoints, let's say P1 equals x1, y1, up to Pn equals xn, yn, with distinct x coordinates. There exists a unique polynomial say f, of degree less than n, such that f of xi is equal to yi for every I between 1 and n. And you can treat this theorem as exactly the generalization of the fact that between 2 points, also over fp, there exists exactly one polynomial of degree 1, right? It's like if you have n points, there exists a polynomial of degree less than n, a unique polynomial that passes through these points. And the proof of this theorem, which I will not do, but it's basically you write n equations in n variables and you find out that there exists a unique solution. And these are the unique solution is the coefficients of your desired polynomial f. And moreover, there is a formula. You take, let's say, for any I 0 between 1 and n, you calculate a specific polynomial Li0 of x. This is you take product of x minus xj, where j runs over all indices between 1 and n that are not I0. And you mod out by the product of all expressions of the form. This is now just a product of coefficients xi0 minus xj, where again j runs over all the indices that are not I0. And then the final polynomial, the Lagrange interpolation, is sum yi l I x. I runs from 1 up to n. Up to n minus 1, right? So here it should also be. Yeah, okay. So, no, here this would be n. Yes. The formula is not going to matter that much to us. It's just I'm putting it here for convenience. What I need you to understand, this Lagrange interpolation is a very powerful tool in everything in many things we do in cryptography, simply because we use polynomials all the time. One of the things that I don't think I will have time to expand on, but this is a polynomial commitment. And the Lagrange interpolation is a very useful tool for working with polynomials, which bring us to what I wanted to discuss today, really the application of the mathematics we did into some kind of algorithm. This is the fast Fourier transform. And here, and again, think about the fact that we use polynomials in cryptography all the time, and we do operations with polynomials. And these operations, they need to be fast as we can. So, yeah, and maybe, let's say, okay, I think maybe it's a good time to take a break, or maybe questions and then a break. and start the fast Fourier transform afterwards. Are there any questions about these two things, about a group of n roots of unity? And yes, so there are other methods to interpolate apart from Lagrange. Lagrange is particularly useful in cryptographic applications, but it's not by far not the only one. So this depends on your application, but for the vast majority of the cryptographic application, we use Lagrange interpolation. The reason is this simple form as a sum of polynomials is very convenient for applications. Any other questions before we take a break? Okay, then
We have one.
and what? Yes. Okay. So what efficient means when interpolate? Look, what you see here, I will touch it later on. But what is the complexity if I give you the points P1 up to Pn? What is the complexity, the time complexity of calculating the Lagrange interpolation? Well, each of the Li zeros would take me O of n. Right? Because I need to do this, I have a product of n factors and so on. And I need to do n such. So the overall complexity is going to be of calculating L of x is going to be O of n squared. Okay, it's for big N, it can be substantially complex, but usually what we have is we have a big prime, and the N is not that big. The prime is very big. It's like maybe 300 digits. It's intractable, but the N is not that big. Okay, so let's take a break of 10 minutes and see you again after that for the fast Fourier transform. So the fast Fourier transform is, in my opinion, it's the most important algorithm in applied mathematics. It is used all over the place. Of course, there are different versions of it, but it has a version in sound analysis, and our version will be over finite fields, which is useful for cryptography. In fact, it is so robust that it is has been generalized into various highly theoretical constructions in pure mathematics, in theoretical mathematics. And so I hope you can appreciate the algorithm is very simple, and we have all the information, all the tools that are needed to understand it. We might go a bit over time if I want to cover all of it. So I'll try to be quick, but still stop me if you have any questions. So the story here is like we have two representations, or let's say I start with a polynomial over Fp of degree less than n. And I have two representations, at least two, of F. One is the sampling representation, or maybe let's say the first one is the vector. Vector representation is, well, F it can be thought of as a vector of its coefficients F0 up to Fn minus 1. Maybe some of the coefficients, maybe fn minus 1 is 0 and so on. I don't care. So this leaves in fp to the n, the Cartesian product of fp with itself. And what Lagrange interpolation tells us is that if you had this polynomial and you had a sampling a given x, which is x1 up to xn, some subset of fp, this is called the sampling set. Of course, if you had the polynomial, then you could evaluate it on all the xi's, you get some yi's, and as a result, you get points x1, y1 up to xn, xn, yn. These are points that if I had a polynomial f and I would do this sampling procedure, then this polynomial would pass through these points. But conversely, if you give me any 2 points, any n tuple of points, then by Lagrange interpolation, there exists a unique polynomial f of degree less than n is such that f passes through these points, namely f of xi is equal to yi for every I. Okay, so we have these two representations, possible representations of a polynomial f. Let's say f is maybe write it here. F of x is sum fi x to the I equals 0 up to n minus 1. And now, when we deal with polynomials, we have 3 basic operations. One of them is you add 2 polynomials. So if I give you 2 polynomials, let's say f is sum fi x to the I equals 0 up to n minus 1, and g is sum gi x to the I, or maybe gj, maybe it would be clearer, gj x to the j equals 0 up to n minus 1, then you can add these 2 polynomials. So if you are in the vector representation, I mean, this polynomial f is just this vector f0 up to fn minus 1, and this is g0 up to gn minus 1. And you can, so in the vector representation, you just do f0 plus g0 up to fn minus 1 plus gn minus 1. And this is your vector representation of the sum of f and g. When you want to add in this, if I give you the polynomial in the sampling representation, that is slightly different. So in the sampling representation, or you know what? Let's just do all the operations So we have addition, we have evaluation. In the vector representation, I have I can write f of x as this is called the Horner rule, I think. I can write it as f0 plus x f1 plus x f2 plus x fn minus 2 plus x fn minus 1. And if you give me a in f, I can plug it into this formula and evaluate the polynomial in complexity O of n. Right? You see that using this formula, you have n operations. So if you give me f in vector representation using the Horner rule, using this formula, I can in the vector representation, I can do it in O of n. Also, addition I can do in O of n. But multiplication of f and g, it takes me O of n squared. I don't want to spend time to write the formula again, but if you look at the formula, it's very easy to see that it's n squared complexity. Now, when I say complexity, I really mean, for simplicity, is like the number of field operations, either addition or multiplication. I count each addition and multiplication, I count as one unit of time. And when I write O, I mean, this could be 3n square, or it could be 5n square. All of them I call them n square. It's like the order of magnitude is n square. But when I go to the sampling representation, so here, let's say, what do I need to do in order to evaluate? In sampling representation, if the element in the field that I want to evaluate the polynomial does not belong to the sampling set, then I need to use Lagrange interpolation in order to construct the polynomial. And constructing the polynomial with Lagrange interpolation, we said it would take me n squared. And after I construct it, then I evaluate the resulting polynomial. I evaluate it in A. It would take me O of n. So all in all, this is order of magnitude is n square operations. But if I want to, let's say, add, I have two polynomials, f and g, and let's suppose that in their sampling representation, they have the same x coordinate. So f in the sampling representation is x1, y1 up to xn, yn, and g in the sampling representation is x1, z1 up to xn, zn. Then, if you want the sampling representation of f plus g, then you can simply do x1, y1 plus z1, xn, yn plus zn, and I claim that this is going to be the sampling representation of f plus g, because when you substitute in f plus g you substitute xi. This is the same as saying f of xi plus g of xi, and assuming that we had sampling representation, then f of xi is yi, and g of xi is zi. And so I get that f plus g evaluated at xi is yi plus zi. So this thing in yellow is the sampling representation of f and g, f plus g. So you see, I did it in O of n. This is O of n. And multiplication, I do the same, but I need to make sure that the degree of f and the degree of g are small enough so that f times g is not going to exceed degree n. So if f and g are of degree less than n over 2, then given the same sampling representation of f and g, I can do the same trick. I do x1 y1 times z1 up to xn yn times zn. And this is the sampling representation. This is going to correspond to the sampling representation of f times g. Because when you do f times g and you evaluate it on xi, what you get is f of xi times g of xi, which is yi times zi. Okay, so the multiplication here I did in O of n, assuming that the x coordinate of the sampling representations of f and g are the same. Okay, so now I have this kind of weird a trade-off that if I do in vector or in sampling representation, I have add, eval, or let's say add, eval, and multiply, then the complexity in each of these things is vector. This is O of n. Evaluation also takes me O of n, but multiplication takes me O of n squared. In sampling, adding and multiplying takes me O of n, but evaluation in the worst case, I mean, if I need to evaluate outside the sampling set, this is O of n squared. And so what do I want? I want a way to move from vector to sampling representation and back. This the way to move it is called the discrete Fourier transform. And I want to move from sampling to vector or vector to sampling representation in less than n squared. And if I can do it, then all my operations, I will never need to waste n squared complexity on my operation, because if I want to, I can just move to the representation that takes in which this operation takes O of n. Moving to this representation takes me less than n squared, and then I'm in business. So that's so the algorithm FFT algo to calculate DFT, this transformation, in fact O of n log n. Okay, so that's the purpose of what we're trying to do. Questions so far? Yes, f0 is the constant. Yes. Okay. So how do I? FFT is an algorithm. It is an algorithm that is called a divide and conquer. And divide and conquer algorithms, they have three stages: divide, conquer, and combine. Okay, so how do I do the division? The division here. So let's say I'm going to explain now how to move from vector representation to a sampling representation. And we'll do the other direction later on. So say from vector to sampling. I start with a polynomial f of degree less than n, but it is given in vector representation. So I will write it like this: f vector, and this is f0, f1, up to fn minus 1. And I need to do the divide. So the divide, I take the even coefficients. So I write f even vector. This is all the guys in even places: f0, f2, up to f n minus 2. So here I forgot to say, this is I'm going to describe a divide and conquer algorithm. And in divide and conquer, we divide the things into two, and then we divide it again, kind of recursively. So it is useful that the size of the input that we start with would be a power of 2. So and I assume that n is a power of 2. It's not a big deal, because if you have polynomials that are of degree not a power of 2, you can pad their coefficients, I mean their vector representation, with 0 until they become vectors of size a power of 2. And since we take we do calculations in FP, and we do it when the degree is a power of 2, I need to assume that P is not equal to 2. Okay, so these are two assumptions. The first assumption is not strict. I mean, I could have done it with n that is not a power of 2, but I cannot have P equals to 2. But that's okay. Anyway, we pick usually primes that are very, very large. They are not 2. So at the divide stage, I divide f, the vector f, into the even guys and the odd guys. So this is f1, f3, up to fn minus 1. Right? N minus 1 is odd because n is even. And I observe yes, I observe, so these guys, they live in f less than n over 2. These are vectors of size n over less than n over 2. Oh, in fact, exactly n over 2. And as a result, each of them corresponds to a polynomial. What is the polynomial that Fe corresponds to? That's a bit tricky because Fe as a polynomial, now I have only n over 2 coefficients. So the polynomial it would correspond to is a polynomial of degree n over 2. And it would look like sum f of 2i x to the I equals 0 up to n over 2 minus 1. Okay, this is, if you translate from such a vector into a polynomial, then you multiply, you have this free coefficient, you multiply the first coefficient with x1, x to the 1. So this is f2 times x to the 1. And so on. So in general, you have f2 to the I, x to the I. And similarly, if you do the translation of FO, then you get f 2 to the I plus 1. Yeah, plus 1, x to the I goes from 0 up to n over 2 minus 1. These two things are polynomials of degree less than n over 2 in the variable x. And so this is the divide part. Conquer well, what do I need to do? So I need, in order to go through the sampling representation, I need to evaluate f on the sampling set x. So instead of evaluating f on the set x, namely to get fx1 up to fxn, these are the y1 up to yn, I will evaluate fe and fo on x squared. X squared is the sampling set where you square all of the elements. And but this needs to be continued, right? Because I will need to do some recursive. So to be continued. If I am able to evaluate the polynomial fex and fox on the set x squared, then what I can do in the combined stage, I can do, I observe that f of x is in fact f even of x squared plus x fo of x squared. And this I leave you as an exercise. It's a very easy exercise calculation. In particular, for every I, f of xi is equal to f e of xi squared plus xi FO of xi squared. So you see, using this formula in yellow, if I want to get f of xi, because I want the sampling representation of f, it is equal. I can equally well just do fe evaluated on xi square and fo evaluated on xi square as well, and then I sum. I do the formula here on the right, and I know that I get f of xi. So if I was able to do the conquer stage to evaluate f of e and f of o on this set, this strange set x square, all the squares of the original sampling set, then I'm in business. I can calculate f of xi. Okay, so let's expand on the conquer stage. What I do, I said, I do recursive steps, right? So I start with my polynomial f. I divide it into fe and fo. These are two polynomials. If you want, I would put x, but I think it's nicer like this. And fe, I also divide into fe and f odd of fe, of this big fe. And I keep going until I reach the last stage of division into fe and fo. What is this last stage? This last stage is when the degree of fe and fo are 1. So here the degree of f is n. Here the degree of fe and fo is n over 2. And here in the last stage of my conquering adventure, I get fe and fos that are of degree 1. Now, how many stages do I have? I have the height of this tree is log of n. Is d equals log of n, right? Because n is 2 to the d. Okay, so I have these stages. Now, what happens? So at the last stage, this is the this is step number D. Here above it is step number D minus 1. What do I have in step number? So how many polynomials of degree 1 do I have in step number D? I have n polynomials. So in step D, we have n polynomials, n degree 1 polynomials. And we need to evaluate in step D to evaluate these polynomials on a set x 2 to the d, which is xn. Right? Every level, every step that I go in the recursion tree, I need the conquering method is telling me that I need to evaluate the fe and the fos that I get on the sampling set square. So each time I do square, this is, I have d steps, so it's x to the n. So now if the size of x to the n is approximate, is of the order of magnitude of n, then simply the complexity step d will take, well, I need to evaluate n degree 1 polynomials on a set of size n. This is n squared. So I'm not gaining anything from this. I mean, we are in this business because we want a way to move from vector to sampling representation in less than n squared. Otherwise, all the operations we care about, we can only do them in n squared times. But on the other hand, was there any question? I heard some. Is this clear? I feel that I might have. Okay, in the conquer step, if we have already split them into even and odd in level 1, how can we split them further into even and odd? Well, because you take FE, the splitting is happening on the vector level. So you take the polynomial, you convert it into a vector, and you take the even and odd coordinates of the vector. So if, I took FE, now I have the FE vector, and now this is the odd coordinate, and this is the even coordinate. Okay, so I can split it into even and odd coordinates and get polynomials f even and f odd according to this split. Is this clear, Ashton?
Yeah, so the even and odd, as in even odd indices, right? Not just even odd values.
Exactly.
Okay,
The even and
got it.
odd
Thank you.
is referring to the indices in the vector representation. This is why I want to distinguish between the polynomial and the vector.
Got it. Thank you.
Sorry?
No, I just said thank you.
Okay. Yeah. So look, we are kind of stuck because, I mean, assuming that the set of the sampling set, even if I raise it to square and so on, is not getting smaller, then simply the last step of my algorithm of my conquering stage would already take me n squared. So it's not worth it. However, if we find x such that x to the 2 to the k, for any k between 1 and d, x to the 2 to the k is kind of a shrinking set. That is, the number of elements of x to the 2 to the k is going to be n over 2 to the k. Really shrinking. If you raise, it's like you have a set x, you raise it you raise all the elements in it by 2, take the square of all the elements in it, and you get a set of size n over 2. Okay? It's a very special property. It's kind of shrinking. Then I claim that now we're in business, because in step D, what do we have? We need to evaluate n polynomials, degree 1. It's just degree 1 polynomial. So you just plug in the value x on a set of size x to the n. It has size n over n, which is 1. So only on one element. So this is complexity O of n. In step d minus 1, if I go up the recursion tree. So what happens in step d minus 1? I have instead of n polynomials, I have n over 2 polynomials. So here it was n, maybe in yellow. Here it was n polynomials. Here I have n over 2 polynomials. They are also degree 1, because if you look at it, once I calculate, if you take one of them, let's say f, I will call it here f, okay? It's like, or f bar. But f bar is equal, f bar is equal to f bar of x is equal to fe of x squared plus x of fo of x squared. And assuming that you already did step D, you have these values, fe of x squared, fo of x squared, for any x in the sampling set. So to calculate f bar is, I mean, f bar is also just a linear, a degree 1 polynomial if you express it with the previous data of calculation that you obtain from step D. Okay, just x times some coefficient plus some free coefficient fe of, and so in step D minus 1, need to evaluate n over 2 degree 1 polynomials on a set x to the n to the 2 d minus 1, which is a set of size by assumption n over 2 to the d minus 1. This is equal to 2. So I have n over 2 degree 1 polynomials. I need to evaluate it on a set of size 2. Okay, the complexity is O of n. Of n over 2 times 2 is O of n. And so on. So for any step, I will have complexity O of n. O of n here. I don't know where to write it. O of n here. O of n here. And so on. And so once I climb back the recursive tree, in order to calculate f with all the previous information, f will be just a degree 1 polynomial with expressed with the coefficient fe and fo. And so it will take me also O of n to calculate, to evaluate f on all the sampling set. Since the size, the height of the tree is log n, I get complexity overall complexity O of n log n. Okay, so now the big question is how to find the set x. And I claim, or before I do that, any questions on this? Assuming so what I did here is assuming that we have a set X with this shrinking property, then I can find an algorithm in n log n to evaluate, to do from go from vector to sampling representation. Yes, exactly. The splitting, so the way the algorithm works is you split in the vector representation, and then you split again until you get to the bottom. And when you get to the bottom, you start to evaluate, and once you evaluate, you go up the tree. Okay, until you can evaluate f on the original sampling set X. Any other questions? This is kind of I mean, we're doing a fast track of it, but I claim you know such an X. Take X to be the set of n roots of unity over the prime field FP. We know that this is a cyclic group. So this is, you take some primitive root of unity, and you can write this set of roots as W0, which is 1, W, up to W to the n minus 1. Okay, this is the set. This is the set of n roots of unity. It's not exactly in FP. So I need to go to a big enough extension in order to have this sampling set that has the shrinking property I'm looking for. But why would it have the shrinking property? Look at X squared. X squared is W0 squared, which is 1. W1 squared, so this is W squared, up to, let's put it this way. Up to a W to the n minus 2. And then I have W to the n, but W to the n, because W is a root of unity, W to the n is 1. And then I have W to the n plus 2. But W to the n plus 2 is just W to the n times W squared, and W to the n is 1, so this is W squared. And I repeat until W to n minus 2. But W to n minus 2 is going to be equal to W to the n minus 2. So you see what happened in, so X squared is just, I might as well stop writing at this point, because I just repeat myself. So I can write it as W to the 0, W squared, up to W to the n minus 2. Okay, this is a set of size n over 2. Moreover, I take any guy in this set X squared, let's say W to the 2k, and I raise it to the power of n over 2. What do I get? I get W to the k times n, which is the same as W to the n to the k, which is 1 because W to the n was originally 1. So In fact, what I got here, x squared, is the set of n over 2 roots of unity. So it's a beautiful phenomena. It's like I found a set. This set is so special that once I raise it to the power of 2, I get the set, the roots, the n over 2 roots of unity. Okay, so now I basically I finished the algorithm because I have the set with the shrinking property that I want, and it's I mean I described the algorithm to do it in n log n.
Nice.
Now, yes. Now we're not. I'm sorry. I want to continue if maybe a few more minutes, maybe 10 more minutes, to describe, because there is a question of how do I turn from sampling representation into vector representation. How do I do that in n log n? What do I need to invent a new algorithm? So the answer is that I don't need a new algorithm. I just write my algorithm in a matrix form. Converse direction, or maybe from sampling to vector. So here I first observe that if you give me the vector representation and you give me this root of unity, primitive root of unity W, then I can write, let me write it like this: 1, 1, 1. And here it's going to be W squared up to W n minus 1. And at the bottom of the thing, I have W to the n minus 1, W to the 2n minus 1, up to W to the n minus 1 square. Okay, this is a matrix. It's called, well, if I multiply this matrix, I mean, these are, if you wish, what you have here is, this is x1. Oh, sorry. Here you have x1 square up to x1 to the n minus 1. And here you have x2 sorry. Have the yes. So this is apologies. So this is x1 0 up x1 1 n minus 1. Okay, x2 0, x2 1, x2 n minus 1, and so on. And if you multiply it by f0 up to fn minus 1, you do the matrix vector calculation, you will find out that you will get a vector that is f of x1, f of x2, up to f of xn, and that's the same as a y1 up to yn. Okay, so in fact, the passage from vector to sampling representation can be done by matrix vector calculation. Of course, this is an n by n matrix, and to do n by n matrix times a vector in a naive way would take you n square operations. This matrix is called the van der Moord matrix. Van der Moord matrix of the sampling set X. The sampling set X is just all the powers of W. So this is W0, W up to W n minus 1. Okay? And what we described is a way to, so this, let me write this guy as F vector transpose, and this guy as Y vector transpose. And what we described, I mean, we simply the passage from vector to sampling is this matrix operation Vx times Ft, and then you calculate, you get the Yt. And Vx, this is sometimes actually in this case that you choose a W, this is called VW sometimes. So VW, we write it here. And we described an algorithm to calculate this guy in O of n log n. For any W that is a primitive root of unity, a primitive nth root of unity, and any vector f, we described an n log n algorithm to calculate the multiplication. Now, there is a proposition that says that the inverse of the matrix W, of the matrix V, is simply 1 over n with the van der Moord matrix of W to the minus 1. And I will not prove it, but it's a very basic calculation. So what you get is that, I mean, just now transform this green equation into the yellow equation looking this way. Ft is equal to V minus 1 W Y T. And this is the same as saying F, the vector F transpose, is equal to V to 1 over n V W minus 1 Y. And we have an algorithm to compute this guy in O of n log n, because we just described how to compute a van der Moord matrix with respect to a primitive root of unity times a vector in n log n operations. So I can so if you give me the sampling representation, namely you give me W and you give me Y, then I take W minus 1, it's also a primitive root of unity, and I calculate in n log n just the same algorithm. I calculate and I get to the vector representation F. So we have exactly what we wanted. I hope that this was useful. But I'm happy to take any questions and requests. For the next time, what I want to start talking about is elliptic curves, but I am open to other requests. Other questions? I mean, I know I did it fast, so so clearly there must be some questions.
Yeah, it's been a lot. I'm sure there might be some. Let's give it a few more minutes, maybe, for people to come up with something. Um, and we can conclude it after. Anyone has any thoughts, feel free to raise your hand, or if you just have any comments. Lee.
Yes, Lee. Yeah.
Yeah, I have a question with calculation for the overall complexity of the
Hmm.
FFT, and you write like over 2 times 2, and can you explain that part?
Yeah. Here.
Yeah, yeah.
So why? So I go to step. Let's start with step D. I have n polynomials, Fe and Fo's. I call them by abuse of notation Fe and Fo, but if you write it nicely, you should distinguish the Fe and Fo's in each level and each branch. But I have in step D, I have n such guys, right? And I needed to evaluate it on a set. I mean, to evaluate each of them, Fe, this, let's say this Fe here, is some polynomial Fex is like a plus Bx. Okay, it's a polynomial of degree 1. And now I need to evaluate it on a set of size 1, only on x1. So this takes me I mean, to evaluate a polynomial like this takes me 2 operations, right? Or actually 3, because I have x1. I need to multiply it by b, and then to add to the result, I need to add a. So this is 3 operations, and I have n polynomials like this. So this is 3n operations. This is O of n. This so far you understand the complexity?
Why there is a 3 operations? I think there is like a one time and one multiplication and one addition, right? It's 2, right? Oh, it's like individually it's one for
No, you're right. You're right. This is 2 operations. Yes, sorry, 2
okay.
operations. I need to multiply and then add to the result. I need to add the the overall complexity in step D is 2 to the n, and we call it complexity n. Now I go with the information that I gathered from step D. I go to step D minus 1. Step D minus 1, I have this guy, F. Let's call it F, okay? It's kind of abuse of notation. It's not the original F, but it's like in kind of a local view, this is the F we care about. And the F we care about, it satisfies this formula star here. F of x is equal to F of e, and this is with these F of e's, Fe and Fo here. They satisfy the formula F of x equals Fe of x squared plus x times Fo of x squared. In particular, now you have a sampling set. Here you have a sampling set. In fact, x to the d minus 1 is going to be a sampling set of size 2, x1 and x2. Okay? Right? Because we had in step D, we had a sampling set of size 1. Now we go up a step, we have a sampling set of double the size. So I write it x1 and x2. Again, it's kind of abused because x1 and x2 appear somewhere else. And so if I take this equation here and I substitute, so now I need to evaluate this F on these guys, x1 and x2, right? But of course, this x1 square is equal to x2 square, is equal to the x that appear in, or is equal to x, I don't know, 0, that appear in the step D sampling set. So in order to evaluate f on this x1 and x2, by this formula I can evaluate. It's enough to do fe x1 square, fo of x1 square, but this I calculated in step D, right?
Yeah. Yes.
You follow? And then what I need is I need to do basically again two operations. I mean, I have from the previous step. This I have from the previous step, and I need to do x1 times this plus the fe of x1 squared. Okay, so this is again, this is two. It's basically O of one operations. I mean, it's two operations. It does not depend on n. So I have, right? I have, but this is only to evaluate x1. How many x's do I have in my sampling set? In step D minus 1, I have two x's in my sampling set.
Yeah.
So this is the reason for these two. Right? I have n over 2 polynomials of degree 1 like this, and each of them I need to evaluate on 2 points, x1 and x2. An evaluation of a polynomial of degree 1 on a point is O of 1, right? But I have 2 points. These 2 points, they when I go up the stages to D minus 2 and so on, these will grow. This is depending on n. Okay, but it's
I see that now.
okay.
Okay. Yes. Because you need to evaluate fx1 and fx2. Actually, that's a thing that both party will need.
Yes. Okay, so you see, so what I end up is that in every stage I have complexity n, O of n, and then the overall is O of n log n.
Okay. Thanks a lot.
Okay. Any other questions before we finish? All right. So I hope to see as many of you in the next time. We will start talking about elliptic curves, heading towards the BLS signatures, which is a famous protocol for cryptographic signatures used in blockchains all over the places.
Yes, the security of consensus layer, basically. That's amazing. Finally getting to the ECC. Thank you so much, Matan. And for everyone, I just want to remind we'll have recording up probably tomorrow, but also tomorrow we have another session on the ZK and link consensus, and then another one on Wednesday. So this week we have two more sessions. Don't miss them. And thank you so much for making it all the way till the end. We are at 2 hours, 15 minutes here. So it's really great. Thank you so much, Matan. Yeah.